and share my screen. Okay, so we'll finish up protein functionality today and move on to enzymes. We'll see how much I can get done with enzymes, then we can determine what's going to be included in the exam next week. Okay, so I think we were done with gelation. So we'll start with some recap to get us where we were, refresh our memories, and move on. Okay, so what are the three categories of water building up around or interacting with the protein? So unmute yourself. Anybody remembers the categories of water?
Yeah, solubility, water binding, and water holding. So gelation, basically. It's protein, water, protein. And I don't know the third one.
So protein, water, protein, yes. But the question, that is correct in terms of water-protein interactions. What I meant here is the three categories that water, like different levels of water. Remember the isotherm structure. So we have water that is what?
So free water and entrapped water and strongly bound water?
Yes. So that's the kind of what I'm referring to. The strongly bound water, where the water is interacting with the protein via dipole-dipole interactions and hydrogen bonding. So this water is not available for chemical reactions, and it requires higher temperature to evaporate. And it doesn't freeze the same way as the free water. So, and then you have the monolayer. When you finish building the monolayer and then you start having multi-layer. So there you would have some water after, when you start building a multiple layer, you start to have water available to dissolve other constituents and to participate in chemical reaction. And then you have the free flowing water. There's the strongly bound water, there's the free flowing water, and there's also the physically entrapped water in a three-dimensional matrix. Okay. So which type of amino acid interact the most with water or bind more water or the most amount of water?
Charged hydrophilic.
Yes, so charged amino acids. So charged amino acids, so that they carry charge at a particular pH, then they bind the most water, then polar, then hydrophobic. Even hydrophobic amino acid residues do bind water too, so it's not like they don't. Okay, and then we kind of talked a little bit about what's the difference between water binding and water holding. So the water binding is the actual interaction of the water and the protein, whereas water holding capacity is when you form a gel or there is a three-dimensional network, the water that is entrapped within this network, how much this network is able to entrap water. Okay. So what's the impact of pH on solubility in general? Protein solubility in general. So what happened at very high pH versus close to isoelectric point versus low pH?
Close to the isoelectric point, the protein will lose its charge, so it's close to zero net charge, so it will aggregate. But acidic or alkaline, the protein will be more soluble.
Yes. Which is the protein more soluble at alkaline pH, at high alkalinity, or at low pH? Does anybody remember?
Alkaline.
Alkaline pH because of
Tyrosine.
Tyrosine.
go ahead.
The tyrosine, the amino acid that have extra OH, I think.
Yes, extra when you have OH that can ionize at alkaline pH, so it loses its hydrogen, so become negatively charged, and also sulfide groups can also lose their hydrogen and become also ionized. So at alkaline pH, proteins tend to have higher solubility than at acidic pH. Is this the same for all types of protein? So, for example, whey protein compared to soy protein. What's the difference if we think about structure? Somebody hasn't answered before. That one, I give it a go. Remember, we were linking structure to function. So what was unique about whey protein that you can remember?
Is it that it's globular, a globular protein?
It is globular, but what else is important about it?
Has very low surface hydrophobicity.
Yes, it has very low surface hydrophobicity. It's very hydrophilic on the surface. So even around its isoelectric point, if it's not denatured, if it's not heated and it's unfolded, even at its isoelectric point, it remains soluble, because really what reduces solubility is hydrophobic interactions that attract the proteins together. And if you really have low hydrophobicity on the surface, even if you lose charge, you don't have this attractive pull. But if you have some sort of high surface hydrophobicity, even a globular protein can have high surface hydrophobicity, like soy and pea. They're globular proteins, but they do also have high surface hydrophobicity. So when you lose net charge, you don't have any more repulsion, and you have this large surface of hydrophobicity, so the proteins get attracted to each other to hide from water. No more charge repulsion and a lot of surface hydrophobicity, then they get interactions and lead to a low solubility around the isoelectric point, even before denaturation. Okay, so what do we remember about the impact of salt on solubility?
It depends on the type and the amount of salts. Some salts can help the protein to charge up better and interact with water, which is called salting in. And then there
Yes.
are some salts like ammonium sulfate, which shield the charges on the protein and cause protein aggregation, so they reduce solubility. There's also chemotropes and
Yes. Excellent. Yes. So it really depends on the type of salt, the concentration of salt. Some salts enhance at a low concentration, enhance protein water interaction by adding some charge load on the protein and interacting loosely with the protein, allowing water protein interactions. And some salts actually at a little bit higher concentration they interact very strongly with the protein. They shield the charges on the protein. And also they kind of disrupt internal ionic bonding within the protein, causing some sort of denaturation. And then the protein interact with another protein via hydrophobic interaction when there is not a lot of interaction with water. Okay. We talked about, kind of touched upon denaturation and solubility. So when the protein is denatured, mostly the surface hydrophobicity increases. And with that, you have increased protein-protein interaction and less protein-water interaction. So you kind of get lower protein solubility. So what factors can you remember that impact gelation?
Temperature.
Temperature. What about temperature?
So
What do
in
we want to
things-
achieve with temperature? Huh?
And some things like egg whites, it can cause gelation if it's thermally induced.
Yeah, so if we want to talk about thermally induced gel, what temperature should we heat the gel? Should we heat the protein solution to form a gel?
Above its denaturation temperature?
Above its denaturation temperature. So we want to ensure that we make sure that that protein denatured so that we have protein interacting with protein, and also have rate of heating is important so that you don't have really a lot of like fast thermodynamics where proteins are moving fast and interacting with each other and forming insoluble aggregates. Whereas a slow rate of heating can help formation of soluble aggregates, and these aggregates start forming three-dimensional network and slowly entrapping water and forming a kind of a nice matrix, three-dimensional matrix rather than an aggregate. Okay, so that's temperature. What else can impact gelation?
pH.
pH, absolutely. How so? Can you give an example?
Like if you go with the isoelectric point of like whey proteins, I don't know exactly.
Yeah, you're heading. What happens if you're at the isoelectric point? Does it form a gel or an aggregate more like? Anybody would like to answer this?
Aggregate.
Yeah, you would form like kind of an, maybe a gel, but it's more like a turbid aggregate, like not smooth gel. So you want to go away from isoelectric point, but at the same time, you don't want the protein to be too charged, then there will be repulsion. You don't have that protein-protein interaction. So you want to choose a pH where your protein is partially charged so that it has some water interaction, but at the same time, you can get protein-protein interactions. And this could be different for different types of proteins. We usually in our lab, we test protein gelation around 7. It might not be ideal for all proteins too. So we want to keep that in mind. If you're working with different proteins, pH 7 mostly works, but it's not ideal for all types of proteins. May not be ideal. Okay, other factors, can you remember other than pH and temperature?
Pressure.
What's that?
Pressure.
Pressure. Yeah, well, pressure can cause denaturation, but we need other inducing factors than just pressure to form our gel. What's that?
Time. How long you heat the gel.
Yeah, time is important. Usually we kind of try to standardize the time if we're comparing across different protein samples, but sometimes certain types of proteins requires more heating to induce more some denaturation and soluble aggregate formation. And then when we cool down, these soluble aggregates start to form your network. Okay, so other than that, think of other things that can enhance gelation, for example.
Presence
There's
of
also-
other additives like sugar.
Yeah, well, presence of sugar. And what else?
Concentration of the protein.
Concentration of the protein. This is what I was looking for. There are other factors, but protein concentration is very important. Different proteins form gel at different concentrations. So if you take gelatin, for example, at 1% protein, you can form a gel. If you take whey protein between 5 to 10%, and then soy between 10 to 15, and then pea above 15, and so on. So different proteins have different abilities and requires more protein in there to form the gel. Okay, so there's a couple other factors. So I'm just going to relieve you and say sometimes we add calcium ion. It is a divalent ion, so it can form ionic bridges between the proteins. So often we add calcium to milk to enhance the curd formation. Sometimes we add calcium to enhance tofu gelation formation, which is the soy gel. Okay, and I think, yeah, one factor we talked about also last time is presence of proteases. So we want to be careful that we don't have any endogenous proteases that might inhibit, break down your proteins to smaller molecular weights that would be harder to form a gel. And speaking of smaller molecular weights, we want to remember that large molecular weight proteins have a tendency to form gels better than small molecular weight proteins. There are multiple factors, presence of sulfidyl groups that can form disulfide interchange and potentially form irreversible gels. This is related to the last question. So the characteristics of the protein, how much, the percentage of hydrophobic amino acid, the presence of sulfidyl group, all get to tendency to form strong interactions and then irreversible gelation. Whereas when you have a gel mostly stabilized by hydrogen bonding, this could potentially be a reversible gel, and that's like gelatin gel could be a reversible gel. You don't have high percentage of hydrophobicity, you don't have a lot of sulfidyl interchange, it's mostly stabilized by hydrogen bonding, which answers the last question. So now I want to move on. Do you have any questions from last time before we, any clarification that you would like to go over before moving on?
I had a question. In the slide where you show gel strands between wheat, ghee, and rice, where does wheat form? And what is dough? Like dough is a 3D matrix, but I don't think it's a gel.
It's not a gel, it's a viscoelastic matrix.
Okay.
So it doesn't, it doesn't necessarily, a gel entraps water. So you really don't have the entrapment of water in you have water obviously in the system, but it doesn't form a gel matrix. It's a viscoelastic matrix. So the gluten forms a viscoelastic. That's a different structure or texture than a gel. So viscoelasticity is really different than gel formation.
And in the order that you have on that slide, where would wheat come? Because wheat has sulfhydryl groups.
Yeah, wheat is not going to form a gel for you. It's not even there. It's not, we don't test it usually, wheat protein to form a gel. It's insoluble in water. So if you ever try to put gluten in water at pH 7, say, it's insoluble. It won't form
a gel. Okay.
Yeah. Mm-hmm. Yeah, if you just get like gluten, vital gluten, and try to put it in water, it's just gonna clump, and it's not gonna, it's not gonna interact with water at all.
I have a question.
Yeah.
What role do stabilizers have when it comes to gelation, especially in like vegan cheeses?
So stabilizers, what happens there is, if you see here in this vegan cheese, when you add gums and when you have starches, they are the ones that forming the gel network. So the protein is not really taking part in formation of the gel. So you get a gel matrix because of these hydrocolloids and modified starches and such. So if you look at the vegan cheese here, you see your proteins, they are scattered and they're not forming a matrix. So they're not contributing to the gel. They're just added to say, okay, we have protein in there and it's plant-based cheese so that they can put it on the label, but it doesn't really it's not having functional contribution. And this is where research is needed to see how we can enhance plant protein gelation and formation of a matrix so that it can be incorporated higher concentration in a vegan cheese and less of the hydrocolloids and less of the modified starches and all of that. Good. Any other questions? All right, so we'll continue on with functionality, and then I'm going to move on to surface activity or interface type of functionality, which is mostly emulsion and foam. So basically, when you have an emulsion, or when you have oil and water, you have high surface tension, so there will be separation. And same with air and aqueous, you will have high surface tension and there will be no interaction. So we need work first. You need to get some mixing, homogenization. So you need force, you need work to mix these two phases, and you need stabilizers. So you need something that can reduce the surface tension and make the colloidal system stable. Okay, so we have dispersed systems. So if we want them to be stable, we need those surfactants or those molecules that would keep that dispersed system stable. And then we end up with a dispersing phase and a dispersed phase. So the dispersing phase is your continuous phase. And then dispersed phase is your either oil droplets or air embedded into your continuous phase. So emulsions are not necessarily always oil and water. It could be water and oil too, such as butter, for example. So butter has 20% water. So it is an emulsion of some sort. So mostly your emulsion is either oil and water or water and oil. So if it's water and oil, then your droplets are water droplets. Okay, so like I said, we need some work. Let's say if we have a protein that's going to stabilize an emulsion or foam, we need some work. We need to get that protein to unfold, to move to the interface, to form a film around the droplet or the air bubble. So we need that work so that the protein can move to the interface and unfold and start orienting their polar groups to the aqueous phase and the nonpolar group to either the lipid phase or the air phase. So we need that work to get that to happen. So it says here, the statement is entropy driven. What does that mean? So there should be then unfolding. So the work is going to cause breakage of bonding within the protein, and then it's going to increase the entropy. And with that, we're going to continue with the unfolding process and the movement and the reorientation that we are seeking. We need this orientation of hydrophobic to the lipid or air phase, and then the hydrophilic to the aqueous phase. So here's just another image showing that if we agitate, if we try to homogenize and stir or mix or whatever, okay, we can form, like the oil can, form oil droplets and we can get some sort of mixture, but then it's not stable. The surface tension is so high, it's going to separate. If we have emulsifiers, surfactants or proteins, small molecular weight surfactants, or if we have proteins, we're talking about proteins here. So the work can also cause not just the mixing, but also the denaturation of the protein, the unfolding, and the formation, the movement to the interface, and the formation of film around the oil droplets that formed due to our homogenization and work that we have put into the system. So here's just another demonstration where the hydrophilic, well, this is oil and water. oh, sorry, water and oil again. So where your hydrophilic groups are going to orient to your aqueous, and the hydrophobic groups are going to orient to the other phase. Okay, so here's just the relationship between the work and the surface tension. So the higher the surface tension between the two phases, the more work you want. And the more work you do, the higher the change. Delta A is change in surface area. The more work, the more homogenization we put in, force we put in, the smaller the droplets are going to be, and that means the higher the surface area. Okay, and with the smaller droplets, we get more stability, and we'll talk about that in a minute here. So the stabilizers, like I said, can be proteins or additives, small molecular weight additives such as lecithin or mono and diacylglycerol. And the lecithin this is where you have one fatty acid and one fatty acid and a phosphate group, or two fatty acids and a phosphate group. So there are characteristics of the protein that help formation of a stable dispersed system. So if you have a very hydrophilic protein, it's really not going to go to the interface, especially on the surface. If you have a very hydrophilic protein on the surface and very low in hydrophobicity in general, this is not going to adsorb at the interface. The more balance you have, so let's look at this one that looks like a soccer ball. So you see kind of like a well balanced balance between hydrophobicity and hydrophilicity. Then you have better adsorption and better reduction of the surface tension, because you have enough interactions with water and enough interactions with the non-aqueous phase to form a stabilized dispersed system. So this diagram here illustrates what happens when we get a dispersed system in the presence of protein. So you have the ability of the protein to move to the interface, unfold due to the work we're putting in. And upon unfolding, it's going to form the film, which is basically protein-protein interactions now around your droplet, whether it is an oil droplet, water droplet, or air bubble. So if we want to talk just about emulsion, so let's start to talk about oil droplet. So then this film is formed around this droplet, and the thicker the film, the more stable your droplet is going to be. And the more charges you have on the surface, so the proteins, basically their polar groups are going to be oriented to the aqueous phase. So the more charge I have, the more polar groups I have on the surface of that film, the more there's going to be repulsion between two adjacent droplets. So you want this nice hydrophobicity that can orientate to the oil phase, and you still want the polar groups to be also charged enough so that you can get the nice repulsion between the oil droplets or the water droplets in a water and oil emulsion. So the characteristics of the protein that impact the emulsion. Yeah.
Silly question. When you
Go
mentioned the high charge, is it about two different droplets with their own individual high charge that would repel each other?
Yes, so the charge of the droplets, and I'll show you an example later of a research we've done. So when the protein forms the film, you have all of these polar and charged groups of the protein that orientated to the water. So the more of these groups are charged, then you have a higher surface charge in general around your droplet. So you have charge around your droplet. And if this is another droplet, you're going to have a lot of charge, and then they will not come together and coalesce, or it will take a long time for them to come together and coalesce. Does that make sense, Paul?
Yep.
Okay. All right. So we have intrinsic factors and extrinsic factors that impact emulsification properties. If we look at the protein, we talked about we need to have some surface hydrophobicity. It's really important. And the balance between surface hydrophobicity and surface hydrophilicity is important, because you want interaction with the water phase, and you want to have this stable external surface of the droplet. But surface hydrophobicity is important to actually be able to reduce the tension and interact with the non-aqueous phase. Flexibility of the protein. If you have a protein that is stabilized by a lot of disulfide linkages, for example, it needs a lot of work, and you need to break those disulfide linkages to actually make that protein a little bit more flexible, to be able to unfold and then form new interactions with the proteins adjacent to it. Charge, we talked about that, it's important. So the protein also is important to be soluble to form an emulsion. If the protein is not soluble, it's really going to aggregate with each other rather than interacting with the water phase. So it's important that the protein has some solubility. So we need to make sure that the conditions enhances protein solubility. So we might want to adjust pH, we want to adjust salt concentration. So we need to work around the conditions to enhance protein-water interaction, because it's important in an emulsion system. So when we say primary structure as well as configuration, it has to do with your amino acid composition and how they come in the sequence. That would lead to your hydrophobicity to hydrophilicity balance. They lead to also, if you have a lot of disulfide linkages, that makes it harder to unfold. And also it links to the charge that we talked about as well. So that's where primary structure is important, because it really means the amino acid composition and also the sequence in order to form a particular configuration with certain appreciable surface properties. Denaturation. So the ability of the protein to denature, to unfold, is really important. So if there's a protein that resists unfolding, then that's not going to be a good emulsifier. So if we compare in this example here a casein to a globular protein. So when you have a flexible random coil protein, which is a casein protein, I thought I had an image. So this casein protein is open in structure already, and it has very nice balance between surface hydrophobicity and hydrophilicity. And it's kind of like it has pouches, it has ends. So one end of the protein is very hydrophobic and another end is very hydrophilic. So when we talk about daily proteins later, I'll show that. I'll talk more about that. So it's flexible, it's not stabilized by disulfide linkages. So it readily forms an emulsion, more so than a globular small molecular weight protein. But we can denature these globular small molecular weight proteins, and they can get on the surface, but they're smaller. Even in their unfolded form, they're not that as stretched. So more proteins can make it to the surface, to the film. Then you end up getting a thicker film, because you have more proteins around, because they're smaller, so they can get more proteins to form rather than open structure protein. So you might get a thicker film, and with a thicker film, you have more stability. So usually a combination of two types of proteins gets you to a really nice emulsion when you have a combination of a flexible protein and a less flexible globular small structure protein. So you have a nice balance between capacity, how much oil we can emulsify, versus stability. So you always want to look at that balance depending on the application as well. So, like I said, we can change extrinsic factors to kind of get a better emulsion. So in the lab, for example, we test proteins under specific conditions just to compare them. But if I'm really targeting a stable emulsion and I want to really form an emulsion with my particular protein, then I want to work with my environmental conditions, see what can I do to enhance the emulsification properties of that protein, change the pH, add salt, work with the homogenization, homogenize more or less. So we kind of work with extrinsic conditions, the pH, salt. Sometimes we add some temperature to enhance denaturation. And then we work with our processing, the homogenization process as well. Presence of surfactants, sometimes this is not a good thing to add a surfactant to when you have an emulsion stabilized by protein, because small surfactants kind of displace the protein on the surface. So that kind of not necessarily a good thing to add. Oh, let's enhance the emulsification properties of the protein by adding lecithin. No, it's not really a good thing. It's going to displace it most likely on the surface because it's smaller and just a better surfactant. Okay, so when we talk about factors affecting,
what do you mean by displacing the protein?
Displacing. So think about, you have proteins on the surface. So you have your oil and then you have proteins around it. And then you have your continuous phase. If you have surfactants in the continuous phase, they're going to go in and just displace a protein molecule. Or potentially if you put them together before you form the emulsion, the surfactants are going to take more space in that film than the protein because they move faster to the interface and they are better at orientating, especially lecithin. For example, you have the phosphate groups and then the two fatty acids. Okay, so the factors that impact emulsifying properties is how fast these proteins adsorb at the surface. So how fast they can move and get on the surface and start orientating their different groups. Amount of protein adsorbed. So the more protein adsorbed, the thicker is your film, the better is your stability. And the extent of conformation or rearrangement. How much is that protein able to flex and orientate the different groups to the different phases? Again, if you have a very compact protein stabilized by a lot of disulfide linkages, it's not very flexible. It's not going to be easy to orientate its different components. How much it's able to reduce the surface tension, basically, or the interfacial tension, the tension between the two different phases, and its ability to form a cohesive film. So you want that also that protein-protein interaction that occurs to form the film around your droplet, or in this case, it's droplet. In the foam case, is the air. So talking about, when we think about emulsion properties, stability is very important. So it's not just you formed an emulsion, how long that emulsion can remain as emulsion before you have phase separation. And usually phase separation occur gradually. So you have your droplets and then they start potentially coming close to each other and fluctuate. So they can fluctuate and then they coalesce. So that meaning two droplets open up, become one big one. So we usually measure droplet size over time. Then we can see that droplet size might increase because of coalescence. And the more coalescence we get, eventually we're going to get phase separation. So it's either creaming or sedimentation, depending on the two phases and the density difference between the two phases. And then we will either see a cream layer or a sediment formation. So droplet size is important. The density difference between the two phases is important. And the viscosity of the continuous phase is important. So we'll look at this equation here. The V stands for rate of creaming. And then you have the R for the radius of the droplet. So the G is for gravitational force. So when we apply a force, the more you apply a force, the higher is the rate of separation. And then the difference in density. So the higher the difference in density, the higher the rate of separation. And then, however, there is here in denominator, you have the viscosity of the continuous phase. So the higher the viscosity of the continuous phase, the lower is the rate of creaming. So you have those different factors that impact the rate of creaming. And if we think about proteins, so if you have larger proteins or soluble aggregates that you're able to form by processing or thermal treatment, the more you're going to have ability to form protein-protein interactions at the interface and have a strong kind of viscoelastic film, a strong film that resists coalescence basically and breakage. And also, if you have dissolved proteins, so if you have proteins, let's say in the aqueous phase, if your dispersing phase is aqueous phase and it's soluble in the aqueous phase, then you have higher viscosity. That's also kind of add to the resistance to coalescence. Yeah. So these are the components that impact the rate of creaming. So if I want to link structure to function here with regard to emulsification, let's look at casein, which is an open structure protein. Like I said, it has this very nice surface hydrophobicity to hydrophilicity balance. The reason that it has a lot of random coil and not structured configuration, it's because of its high proline, which is a secondary structure breaker. So it has high percentage proline that results in this kind of open structure. So it's very flexible. It doesn't have disulfide linkages. It does have like 1 or 2, but it's not like stabilized by disulfide linkages. So it's a flexible protein and it has nice balance and it has distinct regions that are hydrophobic and hydrophilic. It's not like it has alternating hydrophobic, hydrophilic amino acids. Kind of have regions of mostly hydrophobic and regions of mostly hydrophilic and charged. So we call it highly amphipathic nature kind of protein. So they're natural emulsifier. So there is one measurement we do usually to determine one of the emulsion properties, emulsification capacity. So EC stands for emulsification capacity, which is basically the amount of oil a gram of protein can emulsify. So if we look at casein at a concentration of 0.5% protein, so you form a solution of protein, 0.5%, and then you start titrating with oil and homogenizing. And then I'll show you the image in a minute here. But eventually you get to a number which is, in this case, around 1,800 grams of oil is emulsified per gram of protein. And it forms a nice thick emulsion. If we look at soy, for example, so this is the structure of the most functional protein in soy, which we'll talk about later, which is glycinin. It's globular and really it's a hexamer type of protein. So it's like 6 monomers associated with each other. We'll talk about their structure later under legumes and oil seeds. So they are globular, they're not that open structure, they don't readily get to the interface. They are stabilized by disulfide linkages. So if we look at the emulsion that we can form with soy, it requires at least 1% protein. 0.5% protein won't form an emulsion. So we need 1% protein, and even with 1% protein, we have lower emulsification capacity. If I look at P, it has less of this functional protein. In P, it has a different type of, well, it has the hexameric 11S protein legumin in P, but it has more of a different type of globular protein, which is viscillin. We'll learn about it, a viscillin protein. It has different functionality. So for P, you need 2% protein solution in general to form an emulsion. And it's not even a thick emulsion, but you just form an emulsion. And if you look at the emulsification capacity, it's very low. It's around the 400 grams per gram of protein on average, depending on the source of that P protein. Anyway, so here is just to show you that different proteins behave differently, require different concentration, forms different types of emulsion. Some is thick, some is thin, and some can emulsify more oil than others. All right, so
I have a question.
Yes.
So let's say if I use 2% protein concentration instead of 1%, will the protein emulsify twice the amount? Is it always inversely proportional?
No, there is no linear relationship. Also, depending, some proteins tend to really aggregate instead of forming a film. So if you try to form an emulsion with 2% protein with soy, you might form either too thick of an emulsion, or you could see aggregate formation too. So it's not ideal to do a 2% emulsion, for example, in the way we test emulsification capacity, and the way the homogenization we apply in that method. But for different types of applications, you have different protein concentrations and different oil concentrations to form the emulsion. But there's no linear relationship. It doesn't mean if you have more protein, you have linearly better emulsification properties. It really depends on so many different factors, the structure of the protein, and also environmental conditions, and what other components you have in the system. This EC that I just showed the value of is all under just water. There's no other factors, and same homogenization for all. Then it just, there's no linear relationship. If you add the protein concentration, you get higher EC, no, or half the EC if you have half the amount, because the EC is actually calculated per gram of protein. And it doesn't also mean that if you have 1% or 2%, you're going to get the same amount of oil per gram of protein, because you have different interactions at different concentrations. It's complicated.
Thank you.
Okay. So measurements. So how we measure the emulsification capacity that I just talked about is basically what you do is you form your aqueous solution of the protein, and then you titrate oil at a specific rate, a constant rate, and you use a low-speed homogenizer to form the emulsion. And then you continue titrating until the emulsion breaks. So you see an inversion. So with more oil, the emulsion breaks. You cannot anymore add any more oil. So you stop titrating, you look at how many milliliters of oil you were able to titrate in, and then you calculate the amount of oil per gram of protein that you have. And that is how we determine emulsification capacity. So for emulsion stability, basically, we have kind of an estimated or a method that estimates emulsion stability. So it's kind of, we add reagents so that we see destabilization faster. than what we normally would. If we form the emulsion and let it sit, it takes a long time to separate, and then we don't have time for that. So there is a method that actually gives you differences in emulsion stability when you're looking at different proteins in different conditions. So you basically prepare your protein solution, you add your oil, you add a reagent, the SDS reagent, which gradually causes creaming and faster than usual. And then we measure absorption at time 0 and then after 10 minutes or whatever number of minutes. And we calculate emulsification stability, and we can also determine emulsion activity index, which is how well the protein can get to the surface and emulsify using just these parameters, absorption parameters we get, and specific calculations. So this is an example of recent research where you look at emulsion stability in real state. So without adding SDS, and we don't do prediction, we actually look at form an emulsion under specific conditions, and we look over, we monitor over time the stability of the emulsion by looking at different physical parameters. First, we look at the charge of the on the surface of the oil droplets, which is important. The higher the charge, the better the stability, because you have more repulsion. And it is common based on literature that anything above -30 is a good potentially emulsion as charge for stability. And what we do, we monitor turbidity over time, and we also monitor droplet size over time. So in this case, we accelerate also the conditions of storage by storing at really higher temperature, 35, 40 degrees C, so we can see a change faster than months. So we can see it in days, so in order to look at differences in our treatment or different proteins. So here we look at turbidity changes over time. So as turbidity increases, that means we're getting more, fluctuation and coalescence. And here, this figure here shows the distribution of size of the droplets. The solid line is for time 0, and the dotted line is for day 10. 10 days after 10 days. Some treatments are very stable. You don't see change in size over 10 days of storage. Other proteins, you can see that there's increase in droplet size or the distribution of the droplet size after 10 days. So this is another way of looking at emulsion stability. Looking at emulsions can also be with microscopy. So confocal laser scanning microscopy is one way of looking at morphology and distribution of protein, lipid in a system, and use different dyes. So the most common dye is red dye for oil, and a green dye for protein, and blue if you have carbohydrate. So this is example, dairy cheese. You see very nice distribution of droplets and a nice matrix of protein that stabilizes these droplets in place in this cheese. Okay, I'll finish foaming. I have a couple of slides on foaming, and then we can take a break. So foaming, kind of similar type of principle where the protein needs to be worked to unfold and orientate. In this case, well, still we have potentially the aqueous phase, you have the polar groups, and then your hydrophobic groups towards the air. So we really need to also, induce this work. We need to have some force, some work that allows the protein to denature, get to the interface, and orientate its components. And so usually you either whip, mechanical whipping, or injection of gas, but the mechanical whipping helps with denaturation of the protein. And there are a lot of different foods that are foams, and they are listed here. So again, stability of the foam, once you form the foam and you have the film of the protein around the air bubbles, we have properties that allow for stability of the foam. So you want again to have a thick film, and also you want orientated to the aqueous, polar and charged groups. So this will increase the disjoining pressure, repulsion. So you have groups that cause steric hindrance or repulsion that will potentially enhance this disjoining pressure. So another thing is important is this liquid film between the air bubbles. It can thin over time due to capillary forces. So what can prevent thinning or slow down thinning is also the viscosity of the continuous phase. So the higher the viscosity of the continuous phase, the less the thinning of that liquid between the bubbles. Ways to measure the foam. So we can measure foaming capacity, which we can make the foam and then measure the amount of foam formed and calculate milliliter of foam per gram of protein, or we can do the overrun, which is something that, you know, for ice cream, you do overrun, is looking at the volume of the foam minus the volume of the initial liquid before the foam is formed, divided by the initial liquid volume. That gives you the percent overrun. So either we commonly look at foaming capacity to evaluate the potential of a particular protein to form foam. And we look at stability, like over time. We measure the foam volume after a certain period of time after we formed it, and we can determine the change in the volume of the foam over time to determine the foaming stability. So with that, what we have covered so far, we've covered a lot of grounds, I would say, that gets us really prepared to the next portion of the course. We talked about protein structure, its intrinsic properties, and functional properties and related structure to function. And we talked about how what impacts protein denaturation and how that impacts structure and function. So we covered a lot of grounds. What remains really is looking at different protein sources and characteristics of these different proteins in terms of structure and function. We will do that as kind of the second half. And also what's important is protein modification, other than just denaturation of the protein, how we can modify the structure of the protein to enhance functionality. One form of modification is enzymatic modification. And since we're going to cover this part, there's going to be a section on enzymes, and enzymes are potentially proteins, which we will find out soon. Okay, so the next segment is going to be on enzymes. So I'm going to give you 5 minutes break, or 7 minutes break. So we'll come back at 4:05. Okay. Coming back. Wow, I see we lost a few people. Wonder where they went.
Oh, Pam, I just typed a question into the chat.
Okay.
The internet is down at school.
What's that?
There's no Wi-Fi at school. I think that's why probably
We
all the
lost
connections.
something.
Yeah.
Oh, I see. Okay.
I don't see
So,
anything.
so a question. For determining emulsion capacity, is the point of inversion decided by observation or can it actually be tested for? Oh, yeah. So yes, Devin, it's kind of an observational thing and also a sound thing. There is a very unique sound. So when the shaft is turning and then you are titrating and then you have a specific sound of the shaft as it's homogenizing your solution and oil. And as soon as an oil drop is added and the whole system breaks, you can visually see. And also there is a change in the sound. So who has done recent, let me see, I don't see Brigida or any of my students. Allie's here, but Holly, are you here? Can you hear us?
Yeah, I'm here.
Yeah,
I think the school internet kind of cut out, so we had to switch to our phones.
Okay, so Holly, can you elaborate on the emulsification capacity? When it breaks, you hear a different, distinct sound changes?
Yeah, so you hear like kind of a watery sound, and you can, as you're hearing that sound, you can see it get visibly thinner. So you can, both hear and see the emulsion breaking when you're doing that assay.
Yeah. Okay. Thanks, Holly.
Yeah.
I know that they know better than me because they actually do it every day. But I kind of know that you actually see and hear. Good. Any other questions while waiting for folks to reconnect? I think we have most everybody. Huh?
So with the sound, is there a way to quantitate it or is it just a qualitative measure?
Well, it is not qualitative, it's actually quantitative. So you are titrating at a relatively slow rate. So it's kind of, you have a burette, a large burette, and then you have a pump, and you are titrating the oil gradually as you're homogenizing your solution, your protein solution. So you have your homogenizer going and you have your oil dripping at a really constant rate. And what happens is that an emulsion forms and the oil keeps going and gets emulsified and keeps going. And then a drop or so, all of a sudden, the whole system breaks. Then you stop the titration and then you look to see how much oil you were able to incorporate before you observe that very sudden, unobvious change in your emulsion.
Thank you.
Mm-hmm. Okay, I'll get started. I think we have most everybody back. I'm gonna close this and share my screen. Enzymes. Enzymes are wonderful little, they're not very little, but wonderful compounds. And this is one of my favorite topics. So let's talk about enzymes. Before we get going with enzymes, let's try to determine which of the following is correct. Okay, we see people in the chat. Gosh, why don't I see the chat? When I'm projecting, I don't know where the chat box goes. So just tell me.
None of the above?
None of the above. Okay. Any other opinions?
A.
A. Okay. Anybody sides with Ali or who said none of the above? Was it Redika?
Me. It's Sonali.
Sonali. Okay. Any other opinions?
Is it A and sometimes C?
Is it A and sometimes C? I would want to say no to Devin.
I
but
chose
I
I chose H because I look at the phrase enzymes are proteins. I think that's trying to make a universal statement that enzymes are all proteins. And
okay, so I like
always
where this is going.
I always
So
hate seeing that kind of blanket statement. And I looked up before class, I looked this up and I saw that there are ribozymes. Which are,
you looked ahead. Why did you do that? Okay, it's a good thing to look ahead. But okay, so I wanted to tell the story. You took the thunder out of my story.
I get extra
But
credit on the
anyway,
exam now, right?
huh?
I get extra credit on the exam now, right?
Okay, yeah, that's negotiable. All right, so enzymes are not only made of amino acids, so that's incorrect. And enzymes decrease activation energy, hence they speed up the reaction. So B and C are incorrect. Enzymes are proteins. Let's talk about that in a minute. So yeah, here's just showing you an image that this is the protein portion of a particular enzyme that made up of protein. And there is sometimes the enzyme does not work unless there is a cofactor. And we'll talk about activators. So cofactors or coenzyme, sometimes they bind and they are kind of irreversibly bound to the enzyme. So it has very low dissociation factor, and sometimes they are reversibly bound. So, but once they bind to the enzyme, then the enzyme becomes active. Then this enzyme is basically the not only made up of amino acids, and some enzymes might have other groups like phosphates and elemental elements like needing chloride to work to become active. So they're not only necessarily an actual active enzyme if they're only made up of amino acids. Sometimes you don't need a cofactor. Sometimes the enzyme is just it works without cofactors and doesn't have any non-proteinaceous components. So basically, it's not always true. And this is just an illustration that sometimes you need other factors that are non-protein factors, small molecular biological molecules. Sometimes it's a vitamin even. So sometimes it's a mineral element. Anyway, so let's continue here. This has to do with kinetics. We're going to talk about kinetics, and I'm going to explain why we bother about kinetics. It's very important in industry when we're using enzymes for different applications. It's understanding the kinetics of the enzyme is very important. When we're doing research that involves enzyme, understanding the kinetics of the enzyme is also very important. So we're going to be spending some time on kinetics. Okay, so before you answer this, can anybody remember what Km is? From your food chem, from food analysis, from biochemistry? What is Km? Nobody remembers.
Is that the activation energy?
Activation energy, not quite. No.
The Michaelis-Menten constant.
Michaelis-Menten constant, but what is it in reality? What does it represent? It is the Michaelis-Menten constant. That's why it's called Km. But what is it in fact? What it is? What does it represent? Go ahead. We have Brigida
Velocity
and
of the reaction.
Velocity. No, it's related. Well, it has some relation to the velocity, but it's not velocity.
Is it the speed of the reaction and where the reaction goes to the product or reactant?
So the velocity and speed means the same thing. So it's related to velocity, but it's not the velocity.
Is it
Laura,
is it the intercept? I remember like seeing a graph for Michaelis-Menten, and then there's an intercept, and I think that is Km.
There is an
at
yeah, go
half,
ahead.
the rate of, or the substrate concentration at half Vmax.
Yes.
Is that right?
That is correct, Ali. Thank you. So it is the concentration of the substrate at which we get a half Vmax, the maximum rate of the reaction is half. All right, but what does it tell us? Why is it important to know the concentration of a substrate when we have the rate of the reaction at half Vmax or at half maximum? What is this? Why is this important parameter? What does it tell us about the enzyme and the substrate? I'm glad we're covering kinetics, although you have seen it multiple times in the past because you guys forgotten, and that's okay. I forget too. So it tells us the affinity of the enzyme to the substrate. So the lower the Km, the higher is the affinity, because at lower substrate concentration, we have half Vmax. So if we have two enzymes and one substrate, or let's say two substrates and one enzyme, one substrate A has lower Km than substrate B, then that means that the rate of the reaction goes faster at the same concentration for substrate A than substrate B. So it tells me the affinity. The higher the affinity, the lower the Km. And we're going to talk about this a lot more later. Okay, so when the substrate concentration is much greater than the Km, that means we have a lot of substrate in the system, okay? And it's high. And we have same concentration of the enzyme, but we have much higher, very high substrate concentration. Then, which ones of these is correct? First order reaction with respect to substrate, first order reaction with respect to enzyme, or zero order reaction with respect to enzyme. So first of all, you want to know what's first order. When I say first order reaction versus zero order reaction, just to remind you, first order reaction meaning the reaction is dependent on the substrate concentration in A, or the reaction rate is dependent on the enzyme concentration. So the reaction rate changes with enzyme concentration. And zero order reaction, meaning it's not impacted. The reaction rate is not impacted by the enzyme concentration. So when we have very high substrate concentration, what do you think the rate of the reaction is impacted by?
Shouldn't it be impacted by the concentration of the enzyme? So B?
Correct. So which one of the answers it is?
B?
B. Correct. So what happens is when you have when the enzyme is saturated, so no matter how much you increase the substrate concentration, the enzyme is saturated, so there is no way you can increase the rate of the reaction. But at the same saturated substrate concentration, if you change the enzyme concentration, then the rate of the reaction will change. If you increase the enzyme or decrease the enzyme, that the rate of the reaction will change because you really have high substrate concentration. The rate is no longer impacted by the substrate. So we're going to learn that, we're going to talk about that more, and learn that when I'm using enzymes to measure substrate concentration, I want to make sure I have enough enzyme, a lot of enzymes, so the rate of the reaction is not dependent on the enzyme concentration, but I want to make sure that I use substrate concentrations below the saturation point of the enzyme so that I can determine if the concentration of my substrate in my unknown, so that if the rate of the reaction is impacted by how much substrate there is, so I can calculate substrate concentration based on the rate of the reaction or how much product is being generated. So I want it to be first order with respect to the substrate when I'm measuring substrate concentration. So I want it to be first order with respect to the substrate. So I want the concentration when I'm building my assay to be much less than Km. So I need to know the Km of the enzyme to that substrate. So that's why kinetics is important. I need to know the Km, so I make sure that my concentration, I dilute my samples in such a way that my concentration of the substrate, it's much lower than the saturation point so that I can detect a change in substrate concentration based on the production of the product, which is related to the rate of the reaction. If I want to measure enzyme activity, I want to make sure that substrate is not the limiting factor. So the reaction is not impacted by substrate. I want to make sure I have enough substrate, much higher than the Km value, so that the enzyme is saturated. Then in my unknown, so the concentration of the enzyme dictates the rate of the reactions. Then I can build my standard curve using different enzyme concentrations or activities. Then I can determine my enzyme activity in my sample. So that's why kinetics is important. We need to know Vmax, we need to know Km when we're building an assay, or in industry, if I want to develop, produce cheese, I want to know how much chymosin I need to produce a certain amount of curd per certain amount of time. So I need to understand the kinetics of my chymosin so that I know how much concentration I need to use. I also, if I have inhibitors, I need to understand the kinetics of the enzyme and the inhibitors so that I can either inactivate the inhibitor, or maybe I need to add an inhibitor if I want to make sure a certain enzyme is working, for example, to produce high corn syrup, for example. We'll give examples throughout the lecture, which will clarify the importance of enzymes, kinetics. All right. So let's give some examples about importance of enzymes in general in food systems, or why do we care? Where do we use enzymes related to food?
Shelf life for the product.
Yes. Yes, so I need to either inactivate enzymes to enhance my shelf life, or I need to determine the activity of enzymes to know what my problem is going to be. So looking at quality. Sometimes we want to, give me other examples. So what else? Say that?
For digestibility, like converting lactose in milk.
Yes, so it's processing aid. So we can use it to produce delactose milk. We can add an enzyme that will break lactose into glucose and galactose. Then the people with lactose intolerance can drink that milk. Good. What other examples? Processing aids. Give me more examples for processing aids.
Modifying the starch.
Fermentation.
Fermentation or hydrolysis in general, production of protein hydrolysate. So that's a processing aid. What did Paul say? Didn't hear.
I said modifying a starch.
Yes, of course. So modifying a starch, producing maltodextrins, so producing high fructose corn syrup. So we have to break down the starch into fructose and then use into glucose and then use isomerase to produce fructose. So there you go. You have a lot of enzymes there. Great. What other examples you can think of?
It impacts the nutritional value, like for example, enzymes breaking down anti-nutritive compounds like phytates.
Perfect.
That bind iron.
Exactly. You can, again, processing aid to get rid of certain non-desirable components. Great. What else?
Conversion into other products like cheese, like it's
specific
to.
Yes, production of cheese. We need enzymes. Perfect. Okay, we have enough example for processing aid. What other than processing aid?
Like waste management?
Waste management. Yes. So oftentimes if you have a byproduct or waste that is high in lipid, for example, and it's going down the drainage. You want to have lipase to break that lipid so you don't have clogging. So yes, waste management. What else? Other than processing and waste management.
How about to, like, characterize like the enzyme itself?
Characterization, isolation of the enzyme and characterizing the enzyme so that we can use it in assays. For example, for substrate determination. So I want to determine total starch. I need enzymes so that I can break the starch all the way to glucose, and I can measure glucose even by enzyme assays. I need to measure glucose. So measuring different constituents. Total dietary fiber, I need enzymes to measure total dietary fiber. Malic acid in L-malic acid in apple juice to determine if it's authentic or if it is adulterated. So there's so many different applications of enzymes where we use them to determine constituents. And also we need to understand their activity as well in order to use them as processing aids. So determining their own activity and their Km and Vmax for certain substrate that we need them during processing. So isolating the protein and the enzyme, understanding its characteristics so that we can apply it. Sometimes we need to know if there is an inactivation of inhibitors. So how do we test that? We need to have an enzyme assay to test if our processing resulted in inhibition of trypsin inhibitor. For example, in soy, we don't want to have trypsin inhibitor. We don't want to consume that, then we have problem digestion protein. So I want to inhibit trypsin inhibitor, inactivate it, but then I want to test if it was inactivated or not. So I need an enzyme assay. So here you go. So there's a lot of different applications and importance of enzymes. For food quality, we need to determine lipases and lipoxygenases in certain grains or pulses so that we can determine whether there's going to be an impact on flavor during storage, for example. That is one application for quality of food. Okay, so there's a lot of need to understand enzymes. Therefore, we have this section on enzymes, understanding enzymes and their uses. Okay, let's start from the very beginning, ABC. So what's the definition of enzyme? What's the simplest definition of enzyme?
Enzyme is a catalyst that lowers the activation energy.
Okay, it's a biological catalyst, lowers the activation energy, converts substrates to products. Okay, and they speed up the reaction because they lower the activation energy.
And I remember learning that the enzyme itself is not modified, it's not changed.
Yes, so there you go. It's like you have the enzyme here. Once the substrate is converted to product, then you get the enzyme again. So it's not involved in, it's not consumed in the reaction. It might get inactivated over time, but just because of excessive use and processing conditions, if you have, let's say you're using enzyme and during processing, you might not be able to retrieve it all the time, or it might lose activity all the time. Okay, so history. Are enzymes proteins? The big question. So before the 1920s, people thought, yes, enzymes are proteins. And then research started occurring where they were able to isolate the enzymes. And then there was a debate between a German scientist, Willstatter, and between an American scientist from Cornell, Sumner. So here's the story. Willstatter was able to isolate horseradish peroxidase. That was the enzyme that he was working on. So they purified it to an extent that the solution that they ended up with, it has very high activity, but they were not able to detect any proteins. They measure protein and they don't detect protein. So then he concluded that enzymes are not necessarily proteins. At least some enzymes are not proteins. Sumner, however, isolated a protein, urease, I believe the protein was, and was the first to crystallize the enzyme and showed protein characteristics. And then there was a debate over a few years, but the debate ended when Sumner obviously won Nobel Prize, stating that yes, enzymes are proteins. And can somebody tell me why Willstetter, their research was, they were not able to detect proteins in their isolated solution? They didn't do anything wrong, they just didn't detect proteins. Why do you think? I'm going to rely on some of my students here to answer this question.
Just a different kind of enzyme with Willstetter?
No. Actually, a horseradish peroxidase is a protein.
Oh.
Why
How did they measure protein?
Aha, Allie. How did they measure protein back then? So whatever the protein method that they used, it wasn't sensitive to the amount of enzyme, because enzymes can have high activity at very low concentrations. So their method was not sensitive for detecting a very small concentration of a protein. So that's why basically they weren't able to detect protein and came to the wrong conclusion. Okay, so now why do I have here structure of ribozyme? Because ribozyme have a catalytic activity similar to protein enzymes. So ribozyme is type of RNA that basically catalyzes the synthesis of proteins. So it helps formation of, the primary sequence of the proteins based on the genetic coding. So then it lowers the activation energy and helps with the synthesis of the protein in a similar way to a protein-based enzyme. So it is an enzyme, but it's not protein. So I put an article on ribozyme under week 7 if you want to learn more about it. But it acts as a biocatalyst, similar way to a protein enzyme. But now the answer to the question, are enzymes proteins? I would say all food-related enzymes are proteins. They have protein and they might need a cofactor, or they have any other non-proteinaceous component attached to them, but all food-related enzymes are proteins. So all the enzymes that we're going to study about are proteins, but not all enzymes in the world are proteins. Okay, so that is the story that Paul burst my bubble about by looking ahead. Okay. All right, so purification of enzymes started in the early 1900s, mostly in the 1930s. There was a boost of just isolation of enzymes, characterizing them, understanding them, and giving them names and understand their activities and function. The way they purified, chromatographic techniques, electrophoresis, we talked about all of those earlier, and also solubility techniques. So I showed you an example of the procedure I used to isolate enzymes in milk and also enzyme inhibitors in milk back when I was at Purdue. It was mostly based on solubility with salt and pH changes and centrifugation and stuff like that. And stability differences like, denaturation, temperature, and stability under different pH and salt conditions. So this is very common. These techniques are very common to isolate, purify protein, enzymes. So there are a lot of enzymes out there. I would say even more than 3,000 enzymes have been purified and characterized and given names and given EC numbers. I will get to that in a minute. So people started looking at the enzyme structure and understanding also knowing the primary structure mostly by gene sequencing, looking at the gene sequence and trying to determine the protein that will be synthesized from these genes, and also the leather sequencing by MALDI. So understanding primary, and then secondary and tertiary mostly by NMR. And they found that there are homogeneous enzymes that made only from amino acids, and heterogeneous that might have other components. Could be could be glucosylated, like having a carbohydrate moiety attached, or having a phosphorus group, or even having the cofactor that is irreversibly attached to the protein. That could be a vitamin, for example. Okay, they can synthesize enzymes, obviously, and express them in different microbes using gene isolation of gene and inserting the gene in the organism and then expressing the enzyme to produce pure enzymes. Okay, nomenclature. So there basically enzymes have either scientific names, and they have common names, and they have systematic names. So you will, and they have something called EC number, which is every enzyme has an enzyme commission number. So when an enzyme is characterized and understood, and its activity and it is known, then it's given an EC number. So enzymes have common names. So for example, trypsin means nothing. You don't know if, when you hear trypsin, you don't know if it is, unless you know, but people might not know, is it a hydrolase? It hydrolyzes proteins, it hydrolyzes carbohydrate. What is it? It's trypsin. So it's common name, papain, pepsin. So this name doesn't tell you anything about the enzyme unless you know this enzyme. There's also the systematic name, which tells you a little bit about the enzyme. So the name of the substrate is part of the enzyme. So for example, lipase. So it is an enzyme that breaks down lipid. A protease, protein, an enzyme that breaks down protein. Sucrase, enzyme that breaks down sucrose. So the name of the substrate is in the name of the enzyme. Also, the ase, ending with ase, is an indication that it is an enzyme. But then you have different classes of enzymes too. That tells you what they do, basically. Hello, here's a kitty. Tells you what the enzyme does. So oxidoreduction. So you can hear a name of oxidoreductase. Catalase or peroxidase is an oxidoreductase enzyme. So it catalyzes either a reduction or an oxidation reaction. Hydrolase. So you know that water is involved. So basically, in order to break down a peptide bond, for example, a water molecule is added, because once you break the peptide bond, an OH goes to one group and an H goes to another. So H2O, water, is involved. So when water is involved and there's breakage of a bond and pickup of water molecules, then it's a hydrolase. Transferase. So it's when a certain component, functional group, transfers from one molecule to the other. So for example, transfer of phosphate groups, like the D-glucose 6-phosphotransferase, for example. So we take a phosphate group from ATP and give it to glucose in the presence of this enzyme, then you get the transfer of phosphate group. Formation or breakage actually of double bonds without hydrolysis. So that means there's no water involved. So for example, dehydrogenase, so removal of hydrogen groups and formation of double bond, or decarboxylase, removal of a carboxyl group. So this is a lyase type of an enzyme. Isomerization reaction, isomerase, such as the isomerase used to convert glucose to fructose. So you need an isomerase to change, it's an isomer formation. So fructose is an isomer to glucose. Last, you have the ligase, which is basically an enzyme that catalyzes the formation of covalent bonds between two molecules. It's not very common in food application, but it is a group of enzymes. So here are some examples. So the hydrogen peroxide oxidoreductase, it's called catalase, but also can be referred to as peroxidase. The same, catalase and peroxidase, same thing. So you kind of, hydrogen peroxide is broken into H2O and oxygen. So its hydrogen peroxide is reduced basically. We talked about the glucose 6-phosphotransferase and then the lipase. So it's basically breaking off the bond between fatty acid and glycerol. So it's called triacylglycerol acyl hydrolase. It involves water. So when you break that bond, H2O is involved. So if you want to break each of the fatty acids in a triacylglycerol, then you need 3 molecules of water. Okay.
I have a question for the previous slide about the commonly recognized. You said trypsin and pepsin is it like a general enzyme that has so many enzymes under it, or how it is like?
No, it's just a common name. The name doesn't tell you, unless you know that trypsin hydrolyzed protein. You might not know trypsin, it's an enzyme. It doesn't tell you about its activity. It doesn't tell you if it's a hydrolase or if it's a transferase. The name doesn't tell you anything. You either know what it is or you don't. So it's a common name of that enzyme. So trypsin is a protease. So basically it's a hydrolase that breaks down protein, but it's a very specific protease. It has specific, binding sites. Does that answer your question?
Yeah, thank you.
Okay, good. So enzyme specificity. So some enzymes are very specific, some enzymes are less specific. But in general, in order for the reaction to occur, the substrate has to bind to the enzyme. And the binding is stereospecific. It has to have, the binding site has to be recognized by the active site of the enzyme. So you have the active site here, and the substrate has a binding site. So not any part of the substrate is going to bind to the enzyme. There's a specific part of that substrate that's going to bind to a specific part of the enzyme. So one is called active site of the enzyme, and the other is called the binding site of the substrate. So there should be some interaction. Now, is it a covalent or non-covalent interaction that occurs between the enzyme and the substrate?
Non-covalent.
Non-covalent. So it's non-covalent. It's a reversible interaction, and that's why the enzyme is retrieved at the end of the reaction. When the product is formed, the enzyme is released and goes back, and if there's more substrate, can bind to the substrate and continues the reaction. So it is non-covalent, and it might involve hydrogen bonding, ionic interactions, hydrophobic, dipole, or van der Waals. So it can involve any type of interaction, but it's kind of very specific. So in the olden days, back in the 1800s, they thought that, it's kind of a lock and key theory where it has to fit the lock. So the key has to fit the lock. Otherwise, the reaction doesn't form. So it's not only stereospecific, but the active site is rigid. It doesn't change in structure. So it's just rigid. It's a lock, like you have the lock on the door and then the key. Nothing is flexible. But that theory is not correct. So in reality, well, in the 1900s, they discovered that it is really an induced fit, the binding is. So the active site is not rigid site. It can change in structure and it can mold itself to actually be able to bind stereospecifically to that substrate. And what impacts the structure of the active site, as well as the structure of the binding site, is our environmental conditions. So that's why you have to have a specific pH, a specific temperature, a specific ionic strength, and specific amount of water, free water, water activity that is available for the reaction. And that would impact the structure of the substrate and the structure of the binding site. So it's really not a rigid site, and it's impacted by environmental conditions, and it can mold and bend in a way to induce the stereo-specific complex between the substrate and the enzyme. This is important. You're going to say, why do we care? We care because environmental conditions impact the binding, and the way it impacts the binding is by affecting the structure of that binding site, or the structure or characteristics such as charge, as simple as charge, of the substrate as well as the binding site. Okay, so let me see here, a few minutes before I end. I will stop in like 7 minutes here. So enzyme activity. So we want to understand kinetics. So this is the very beginning of trying to understand and get us to the kinetics. So we have what happens when you have a substrate and you have an enzyme. You have two events happening. So you have the binding of the substrate to the enzyme. So formation of the ES structure. So here is you have your enzyme, and then the enzyme binds to the substrate. This is your ES. And then the reaction happens and the product is formed and the enzyme is released. So if we want to think about rate of reaction, so you have three things going on here. So you have the E plus S forming the ES. So you have rate of formation of ES. And then you have the rate of formation of the product. So you have this rate of the reaction, K2, formation of the product. And then you have another reaction happening, which is the reversal, because the ES can also dissociate into E plus S. So you have a rate of appearance. Remember that when we get to the kinetics. So we have rate of appearance of ES, and then we have rate of disappearance of ES. The rate of disappearance of ES is basically this rate over here going backwards, and this rate over here that produces the product. So rate of disappearance is this plus that. We will show the equation later, but you have rate of appearance and you have rate of disappearance. So this is what's happening. And then the chemical conversion is when a substrate converts to a product. Okay, good. Another basic thing to remember is activation energy. So an enzyme reduces the activation energy. By that, the rate of the reaction is multiplied by a lot. So 10 to 3 times, 10 to 3 to 10 to 11 times, you can get a reaction to be, the speed of the reaction to be increased or accelerated. Okay, so The rate of the reaction is impacted by many things, okay, a lot of different things. So of course, enzyme concentration. The higher the enzyme concentration, the rate of the reaction increases potentially up to depletion of substrate. Once the substrate are depleted, that's it, no more reaction. It's also dependent on the concentration of substrate. We're going to spend some time explaining that, the impact of the substrate concentration on the rate of the reaction. And then, of course, there are inhibitors. So the rate of the reaction is impacted by presence of inhibitors to the enzyme. And then cofactors. Also, some enzymes require cofactors. So presence and concentration of the cofactors impact the rate of the enzymatic reaction. And then you have the environmental factors. pH, you have optimum pH that will allow best interaction between substrate and the enzyme. So the rate of reaction on average decreases 0.5 times with every 1 pH unit deviation from optimum. Temperature. So there's also an optimum temperature for the enzyme where you have the best configuration for interaction. And here, in general, the velocity decreases 1.4 to 2 times with every 10 degrees change or decrease in temperature. Ionic strengths. Also, some enzymes require some salt or ions to act, and sometimes some concentration inhibit the activity. So some reactions are formulated in presence of particular ions or salt in order for the enzyme to function. Okay. So we need to understand enzymatic kinetics and how all of these factors impact enzyme kinetics. That means the rate of the reaction in terms of initial velocity, maximum velocity, and Km. These are called kinetic parameters. So we need to understand the kinetic parameters of enzyme catalyzed reaction. Why? Because as I said at the beginning, this is important when we are setting up enzymatic reaction in the lab to either determine an enzyme activity or determine inhibition of an enzyme or determine constituents, or basically use them for as processing aids or waste management or whatever. You need to know what enzymes to use, what substrates to have, how much concentration, so that you can optimize your process or optimize your enzymatic reaction. Okay, since I've reached recap questions, that means I'm going to stop here. All right, which means, what does it mean for the exam? Include or not include? We're not including enzymes in the exam next week. So next week's exam will be through the functionality lectures. Okay, I was hoping to go further, but here we are. All right, lucky you. Any questions before we go? Any questions about the exam? No? If you think of anything, email me, unless you have something now. If not, Ali?
I assume that the exam will be a similar format to like those homework or extra credit assignments.
Yeah, similar. What I will do also, I will look at what I have of a former exam that I can share on Canvas. I will look at that either tomorrow or this weekend, and I will post it so you'll have it in the weekend to look at it as an example. But definitely the homework helps if you solve it, and then there will be the previous exam questions. Of course, there will be different questions, but at least you get a general idea. Okay, all right. Well, I'll see you guys next week. You can all leave, but Laura, may you stay for 1 second?
Yeah, I could stay.
Okay, all I want is to try to determine with you a time where you can teach me how to have a test exam.
I was wondering about that. Yeah. Let's see. When would you like to meet? Like, is this something you want to meet like within the end of this week or beginning of next week?
So I'm gonna try to work on the exam this week yet or the weekend. So if you have time tomorrow, I have time, which is amazing that I have some.
Yeah,
time.
I was gonna say, I thought it was your schedule. What time do you have?
So we can, well, I don't want to mess your day tomorrow if you have plans or classes. So I'm flexible. I have a time opening between 12:30 and 2, but then I have also at 4:30 if you're okay meeting later. So it's up to you really, depending on your day.
Yeah, what if we did right before that meeting, the hemp project?
So I do have 2 meetings before the hemp.
Oh, you said until 2. I'm sorry. Why don't we do then like 1 to 1:30? Would that be okay?
Yes, just send me an invite. If this works for you, then it should
Yeah.
be fine for me. Okay, thanks, Laura.
Yeah, no problem. No problem. I was expecting that.
Potentially can figure it out, but maybe if you show me, then I don't have to spend.
It'll be faster. No, it'll be faster. I'll send you the invite right now.
Okay, thanks, Laura.
Okay, you're welcome. Bye, PM.